There's something haunting about the night sky, the way it stretches endlessly, dotted with stars that seem fixed in place, obeying the rules we've come to accept. But what if I told you some of those distant lights aren't playing by the rules at all? What if entire galaxies, quasars, and cosmic structures are racing through the universe at speeds that shouldn't be possible, defying the very laws physics has sworn by for over a century? This isn't science fiction. It's real, it's happening right now, and it's forcing scientists to rethink everything they thought they knew about the fabric of reality. Welcome to a journey through the cosmos' greatest rebels, 26 celestial anomalies that move faster than Einstein's theories should allow. These aren't just small quirks in the data, they're colossal, universe-spanning mysteries that challenge our deepest understandings of space, time, and motion. Picture a galaxy cluster hurtling away from us so fast that light itself struggles to keep up, or a quasar whose jets blast matter outward at nearly the speed of light, except, according to our math, they shouldn't be able to. How is this possible? What unseen forces are at work? And what does it mean for the future of astrophysics? This video is your ticket to the frontier of cosmic discovery, where the impossible becomes real. We'll explore these speed-defying structures one by one, uncovering the theories scientists are scrambling to test, from hidden dimensions to dark energy's explosive push. But more than that, we'll confront the thrilling possibility that these anomalies aren't flaws in our models but clues to something far grander, waiting just beyond our current grasp. So buckle up. By the time we're done, you'll never look at the night sky the same way again. The first stop on our journey through the cosmos rule breakers takes us to a dazzling enigma, Quasar 3C273. Discovered back in 1963, this brilliant beacon isn't just one of the brightest objects in the universe, it's also one of the most perplexing. At first glance, its jets seem to race across space faster than light itself, a feat Einstein's theory of relativity insists is impossible. So how does this cosmic speedster appear to break the ultimate speed limit? The answer lies in a cosmic sleight of hand. When astronomers first measured the motion of 3C273's jets, they noticed something bizarre. Regions within them seemed to separate at speeds exceeding light by several times. But rather than rewriting physics overnight, scientists realized this illusion stems from the quasar's orientation. Its jets are pointed almost directly at Earth, hurtling toward us at near light speed. Imagine watching a spaceship zooming straight at you with a spotlight. If it's moving fast enough, the light it emits later has less distance to travel, making it appear as though the spotlight's beam moves impossibly fast across your field of view. That's the essence of what we're seeing here. Yet even with this explanation, 3C273 doesn't let us off the hook that easily. The precision required for this illusion to work is razor-thin, raising questions about why so many quasars seem perfectly aligned to create this effect. Some theorists speculate hidden mechanisms, perhaps unseen forces nudging these jets into alignment, or even stranger possibilities, like space itself behaving differently on cosmic scales. Others wonder if we're glimpsing a deeper truth about relativity, where extreme conditions reveal wrinkles in our understanding of motion itself. What makes this quasar truly extraordinary isn't just its apparent defiance of physics, but the way it forces us to question our assumptions. Every time we think we've solved its mystery, it reveals another layer, another puzzle waiting to be unraveled. It's a reminder that the universe doesn't exist to conform to our models. It's our job to catch up to its brilliance. Now we arrive at one of the most compelling cosmic puzzles, the bullet cluster. Here, two galaxy clusters have collided in a spectacular, slow-motion wreck unfolding over hundreds of millions of years. But this isn't just a cosmic fender bender, it's a window into the invisible scaffolding of the universe. What makes the Bullet Cluster extraordinary isn't what we see, it's what we don't. When astronomers first studied this collision, they expected the visible matter-hot gas glowing in X-rays to align with the bulk of the mass. Instead, they found something startling. The gas, slowed by friction, lagged behind, while the galaxies and something far more mysterious raced ahead. That invisible something revealed itself through gravitational lensing, bending light from background galaxies in ways that betrayed its presence: dark matter. The Bullet Cluster became smoking gun evidence that dark matter isn't just theoretical, it's real, it's here, and it's behaving in ways that defy expectations. But here's where things get even stranger. The speed at which these clusters plowed through each other, over 7 million miles per hour, should have been impossible under standard gravitational models. It's as if someone pressed an unseen accelerator, flinging dark matter forward like a slingshot. Some scientists speculate that dark matter might interact with itself through forces we've yet to discover, creating a kind of cosmic push that amplifies its motion. Others wonder if we're seeing the fingerprints of dark energy, the same mysterious force driving the universe's expansion, acting on smaller scales. The Bullet Cluster doesn't just challenge our understanding of dark matter, it turns the mystery inside out. If dark matter can zip through space faster than gravity alone should allow, what else is it capable of? Could its behavior hint at hidden dimensions or new particles beyond our current physics? Every observation deepens the intrigue, revealing a universe far more dynamic and unpredictable than we ever imagined. What's clear is this: collisions like the Bullet Cluster aren't just cosmic accidents. They're laboratories revealing the invisible rules that govern everything. And with each discovery, we're forced to admit how much we still have to learn about the dark, uncharted territories of our universe. Look up at the night sky, find the Andromeda galaxy, a faint smudge of light to the naked eye, and realize this gentle glow is actually a cosmic freight train barreling toward us at 110 kilometers every second. That's over 250,000 miles per hour, a speed so immense it defies simple gravitational explanations. Yes, galaxies collide, it's part of the universe's grand dance, but Andromeda's approach isn't just a leisurely waltz. It's a sprint, outpacing what our models predict should be possible based on the visible mass of our two galaxies alone. So what's propelling Andromeda toward us with such urgency? One leading suspect is the invisible hand of dark matter. The Milky Way and Andromeda aren't just islands of stars, they're embedded in vast halos of this mysterious substance, whose gravitational pull might be accelerating their collision. But here's the twist: some simulations suggest even dark matter's gravity isn't enough to account for Andromeda's breakneck speed. Could there be something else, an unseen river of dark matter flowing between us? Or perhaps a cosmic undertow from the Great Attractor, a colossal gravitational anomaly deeper in space tugging us both toward it? Then there's the bigger picture, the cosmic web. Galaxies aren't scattered randomly. They're threads in a sprawling, invisible structure shaped by dark matter and dark energy. Andromeda's motion might not just be about its relationship with us, but part of a larger current, a flow of galaxies moving in sync across unimaginable distances. Imagine standing in a river, feeling the water pull you downstream, except the river is made of space-time itself, and every galaxy for hundreds of millions of light years is being swept along with you. The implications are staggering. If Andromeda's speed reveals gaps in our understanding of gravity, dark matter, or the large-scale structure of the universe, then its eventual collision with the Milky Way, set for about 4 billion years from now, isn't just a future spectacle. It's a live experiment, a chance to witness cosmic forces at work that we're only beginning to comprehend. And here's the most humbling thought. By the time these two galaxies merge, their stars will glide past one another, rarely colliding, weaving a new galactic tapestry. But the real story isn't the crash, it's the mystery of why it's happening so fast. Every measurement, every simulation brings us closer to unraveling it, yet the universe keeps reminding us there's always more to discover. Somewhere beyond the Milky Way's dusty veil, hidden from our telescope's direct gaze, lurks a gravitational enigma so powerful it's bending the paths of entire galaxies, including our own. This is the Great Attractor, a cosmic heavyweight pulling thousands of galaxies toward it with a force we can measure but still struggle to explain. Picture a river of stars, gas, and dark matter, all flowing in the same direction, as if drawn by a celestial magnet we can't quite see. At the heart of the mystery is scale. The Great Attractor's influence stretches across an astonishing 600 million light-years, tugging not just on the Milky Way, but on every galaxy in our local supercluster. Yet when astronomers calculate the visible mass in its vicinity, galaxies, gas clouds, and star clusters, it adds up to only a fraction of the gravitational muscle required to move so much so fast. So what's generating the rest of that pull? For decades, the leading theory pointed to the Norma cluster, a dense gathering of galaxies near the Great Attractor's suspected core. But even this massive cluster falls short, accounting for less than 10% of the necessary gravity. That discrepancy led scientists to an even grander possibility. The Great Attractor might be just one piece of an unimaginably vast structure called Laniakea, our home supercluster. Picture a spiderweb of galaxies with the Great Attractor as one knot in the threads, a gravitational hotspot where multiple filaments of the cosmic web intersect. Yet even Laniakea's immense scale might not tell the whole story. Some researchers propose an even more radical idea, that the Great Attractor's motion isn't just about what's pulling us but what's pushing from behind. Dark energy, the mysterious force accelerating the universe's expansion, could be creating uneven pressures like cosmic tides that amplify certain flows of galaxies. Others wonder if we're seeing the echo of an ancient collision between superclusters, a billion-year-old shockwave still rippling through spacetime. The Great Attractor's most tantalizing clue lies in its hiding place. Positioned behind the Milky Way's zone of avoidance, a thick band of dust and stars blocking our view, it's like trying to study a mountain peak through fog. New tools like infrared and radio telescopes are finally piercing that veil, revealing hints of colossal structures we never knew existed. Each observation deepens the puzzle, suggesting we're not just missing pieces of the map but entire continents of the cosmic landscape. What makes this anomaly so thrilling isn't just its defiance of expectations but what it represents. A reminder that even in an age of precision cosmology, the universe still holds colossal secrets. The Great Attractor isn't just pulling galaxies, it's pulling us toward new questions, new frontiers, and perhaps one day, answers that could rewrite the story of our corner of the cosmos. Deep in the constellation Boötes lies a cosmic anomaly so vast and empty it defies logic. A spherical void stretching 330 million light-years across, where galaxies should crowd the darkness but instead only a handful remain. The Boötes Void isn't just a quiet corner of the universe, it's a gaping hole in our expectations, a place where the rules of structure and motion seem rewritten. Astronomers call it the Great Nothing, but that name sells it short. This isn't mere emptiness, it's a laboratory for the universe's most perplexing forces, where the few galaxies that do exist race through the void at speeds that leave scientists grasping for explanations. What makes the Boötes Void so unnerving isn't just its lack of galaxies, but the behavior of the ones that linger. These isolated islands of stars aren't drifting lazily. They're hurtling away from the void's center at velocities approaching 2,000 kilometers per second, far faster than standard models of cosmic expansion predict. If the universe's growth were a gentle tide, these galaxies are caught in a riptide, as if some invisible hand is shoving them outward. The question isn't just why the void exists, but why what's left inside seems desperate to escape it. One leading theory points to dark energy, the mysterious force accelerating the universe's expansion. In most of space, gravity's pull balances dark energy's push, but in a void this large where matter is scarce, dark energy might dominate unchecked. Imagine blowing up a balloon with a few tiny dots inside. The emptier the space, the faster those dots spread apart. But here's the catch. Even this explanation doesn't fully account for the extreme speeds observed. Some researchers speculate that the Boötes Void isn't just a passive absence but an active player. Its growth fueled by a repulsive force beyond dark energy, something akin to an anti-gravity effect embedded in spacetime itself. Then there's the eerie possibility that the void isn't empty at all. What if it's filled with an exotic form of dark matter, invisible and intangible, whose gravity somehow repels ordinary matter instead of attracting it? Or perhaps the void is a scar from an ancient collision between universes in the multiverse, a bubble of distorted physics left behind. The most radical theories suggest the galaxies aren't being pushed but pulled by something even more enormous lurking beyond the void's edges, a structure so vast it reshapes the flow of galaxies around it like a cosmic whirlpool. Every observation deepens the mystery. The void's sheer scale challenges our understanding of how structures form. According to standard cosmology, something this large shouldn't exist. Yet there it sits, a cosmic blank spot that refuses to be ignored. For astronomers, it's a reminder that emptiness can be just as revealing as abundance. The Boötes Void doesn't just question our models. It dares us to imagine a universe where the gaps in the map hold the keys to everything we don't yet understand. And as telescopes peer deeper, one thing becomes clear. In the great tapestry of the cosmos, the holes might tell the most compelling story of all. The universe is supposed to play fair, expanding at a rate we can measure, with structures growing in predictable ways. But then there's the Hercules-Corona Borealis Great Wall, a galactic filament so enormous it shatters every expectation. Stretching an almost incomprehensible 10 billion light-years, this cosmic leviathan isn't just big, it's too big, too fast, and too organized for our textbooks to explain. Imagine a single structure so vast it would take light 3/4 of the universe's current age to traverse it. Now imagine parts of it are racing outward even faster than our models say they should. This isn't just a curiosity, it's a full-blown crisis for cosmology. So what makes this great wall so unsettling? For starters, its size violates something called the cosmological principle, the long-held assumption that, on large enough scales, the universe should look roughly the same in every direction. Yet here we have a titanic ribbon of galaxies, quasars, and dark matter, clumped together in a way that defies the supposed uniformity of space. Even more perplexing, some regions within it exhibit peculiar velocities, movements that can't be explained by the universe's expansion alone. It's as if hidden currents are tugging at the fabric of this structure, guiding its growth in ways we can't yet decipher. One possible explanation lies in the shadowy influence of dark energy. If this mysterious force isn't distributed evenly, if it ebbs and flows in unseen waves, it could create pockets where galaxies are pushed apart faster than expected. Picture blowing up a balloon with weak spots. Some areas stretch more than others, but even this idea struggles to account for the Hercules-Corona Borealis wall's sheer scale. Another theory suggests we're seeing the echo of primordial gravitational waves, ripples from the Big Bang so powerful they left behind imprints in the distribution of matter. These waves could have acted like cosmic blueprints, seeding the universe with preferred directions for growth. Then there's the radical possibility that this structure isn't just a filament but a brain, a higher dimensional membrane intersecting our own universe, its gravity warping spacetime on scales we're only beginning to detect. String theory proposes such dimensions could exist, curled up and hidden, but their gravitational effects might manifest in anomalies like this. If true, the Hercules-Corona Borealis Great Wall wouldn't just be a structure, it'd be a portal to a deeper layer of reality. Of course, some scientists argue this Great Wall might be a statistical fluke, a chance alignment of smaller structures masquerading as something grander. But with each new survey, its existence grows harder to dismiss. Telescopes like the James Webb are now probing its depths, searching for clues in the light of ancient quasars or the faint glow of intergalactic gas. What they find could force us to rewrite not just our models of cosmic expansion, but our very understanding of how the universe builds itself, the most humbling thought. This structure is so colossal, so ancient, that by the time its light reaches us, it may have already evolved into something even stranger, a cosmic fossil pointing toward truths we're only beginning to grasp. The Hercules-Corona Borealis Great Wall doesn't just challenge our assumptions, it dares us to think bigger, to imagine a universe where the rules we hold dear might just be the first draft of a much weirder story. The Whirlpool galaxy, with its perfect spiral arms and dazzling swirls of starlight, looks like a textbook example of cosmic order until you focus on its outer edges. There, something strange unfolds. Stars in the galaxy's outermost reaches whip around its center at speeds that shouldn't be possible based on the visible matter alone. It's as if the galaxy's rotation curve, the way its speed changes with distance, has been tampered with by unseen hands. This isn't just a quirk of one beautiful spiral. The Whirlpool's mystery mirrors a puzzle seen across the universe. Galaxies rotate faster at their edges than our understanding of gravity predicts. Normally, stars farther from the center should move slower, like planets in our solar system, Neptune trudging along compared to Mercury's sprint. But in the Whirlpool, those distant stars are racing as if pulled by something extra, something invisible. The leading suspect, dark matter. Most astronomers agree this elusive substance forms vast halos around galaxies, their gravity tugging stars to higher speeds. Yet the Whirlpool adds a twist. Its outer arms aren't just speeding up, they're doing so unevenly, with patches of stars moving even faster than the dark matter model can explain. Some researchers point to tidal forces from its neighboring galaxy, M51, as a possible culprit. Imagine two dancers twirling close enough to grip each other's hands. Their mutual pull could fling one's skirt outward in unexpected ways. But simulations show this interaction alone can't account for the extreme velocities observed. Another theory suggests the Whirlpool might harbor streams of dark matter, filaments of invisible particles flowing along its arms like cosmic currents, adding extra gravitational oomph in specific regions. If true, it would mean dark matter isn't just a static halo but dynamic, structured, and capable of shaping galaxies in ways we're only beginning to map. Then there's the wild card, modified gravity. A small but vocal group of physicists argues that dark matter might be a mirage, that instead, our equations for gravity break down on galactic scales. They propose tweaks to Einstein's relativity, suggesting gravity behaves differently where matter thins out. But even these alternative models struggle to explain the Whirlpool's erratic outer stars without invoking some unseen influence. What makes this galaxy so compelling isn't just the mystery of its motion, but what it reveals about our methods. Every telescope trained on its arms, from radio observatories tracing hydrogen gas to infrared eyes piercing dust clouds, adds a new piece to the puzzle. And with each observation, the Whirlpool whispers the same tantalizing question: are we missing a fundamental piece of physics, or is the universe simply more inventive than we dared to imagine? One thing's certain, the Whirlpool galaxy isn't an outlier. It's a mirror held up to our ignorance, reflecting how much we still have to learn about the forces sculpting the cosmos. And as long as its outer stars keep defying expectations, they'll remain beacons, guiding us toward deeper truths hidden in the dark. The Sombrero galaxy, with its striking resemblance to a wide-brimmed hat floating in space, has long captivated astronomers for more than just its beauty. But peer beyond its radiant disk, and you'll find a mystery lurking in its faint outer halo. Stars hurtling at velocities so high they should have flung themselves into the cosmic void long ago. Yet they cling to the galaxy as if held by invisible chains. This isn't just a quirk, it's a direct challenge to our understanding of how galaxies hold themselves together. At first glance, the Sombrero's halo behaves like any other, a sparse sprinkling of ancient stars orbiting the galaxy's dense core. But when researchers measured their speeds, the numbers didn't add up. These stars are moving too fast, as if the galaxy's gravitational grip is far stronger than its visible mass suggests. According to Newton's laws, stars traveling at these velocities should have escaped into intergalactic space, yet the Sombrero's halo remains intact. So what's keeping them anchored? The most straightforward explanation points to dark matter. Its invisible gravity acting like an unseen hand, reinforcing the galaxy's pull. But here's where things get curious. The Sombrero's halo isn't just uniformly overperforming. It's patchy, with pockets of stars moving even faster than the dark matter models predict. Some regions seem to have an extra gravitational kick, as if dark matter isn't smoothly distributed but clumped in hidden streams or shells. Imagine a spiderweb where some threads are thicker than others, tugging unpredictably on anything that brushes past. Then there's the fringe possibility that we're seeing something even stranger. Could the Sombrero's halo contain exotic matter particles unlike anything in our current physics playbook? Some theorists speculate about self-interacting dark matter, which might collide with itself, creating dense knots that amplify gravity in specific areas. Others wonder if modified gravity theories like MND could explain the anomaly without invoking dark matter at all, though even these struggle to account for the Sombrero's extreme outliers. The galaxy's unique structure adds another layer to the puzzle. Unlike typical spirals, the Sombrero boasts a massive central bulge and an unusually thick disk, suggesting a turbulent past, perhaps an ancient collision that stirred its dark matter into an uneven distribution. If so, its halo could be a fossil record of that chaos, a relic of forces we're only beginning to untangle. What makes the Sombrero so compelling isn't just the mystery of its runaway stars, but what it reveals about the limits of our cosmic maps. Every galaxy we study is a test of our theories, and the Sombrero's halo is failing that test spectacularly. It's a reminder that even the most familiar celestial objects can harbor secrets, whispering hints of a universe far more intricate than we've dared to imagine. As telescopes grow sharper, this galactic enigma may yet surrender its truth, and in doing so, rewrite the rules of gravity itself. The Large Magellanic Cloud has always been the Milky Way's most conspicuous satellite, a ragged, star-studded dwarf galaxy visible to the naked eye from the southern hemisphere. But this cosmic neighbor isn't just passing by. It's racing around our galaxy at nearly 320 kilometers per second, a speed so extreme it's sending shockwaves through astrophysics. According to conventional models, the Milky Way's gravity shouldn't be strong enough to keep something moving this fast in orbit without flinging it into deep space. So why hasn't the large Magellanic Cloud escaped? And what does its breakneck dance reveal about the hidden architecture of our galactic home? For decades, astronomers assumed this dwarf galaxy was a fleeting visitor, destined to drift away after a few loops around the Milky Way. But recent measurements tell a different story. Its orbit is tighter and more stable than anyone predicted, suggesting an invisible tether, something anchoring it far more powerfully than the Milky Way's visible stars and gas can explain. One possibility: our galaxy's dark matter halo might be twice as massive as previously thought, its gravitational reach extending much farther into the cosmic void. Imagine a spider sitting at the center of a web you thought was small until you realized the threads stretched twice as far as you could see, but mass alone might not solve the puzzle. The large Magellanic Cloud's path also hints that dark matter isn't spread evenly around the Milky Way. Instead, it could be clumped in dense, irregular patches, like invisible mountain ranges warping the gravitational landscape. As the dwarf galaxy plows through these regions, it might experience unexpected tugs and breaks, altering its trajectory in ways standard models fail to capture. Some simulations even suggest the Milky Way's dark matter halo is lopsided, a cosmic asymmetry sculpted by ancient collisions with other galaxies. Then there's the wild card: the large Magellanic Cloud might not be orbiting alone. Recent studies reveal it's likely dragging a trail of smaller satellite galaxies, all bound together in a cosmic convoy. This entourage could be stirring up the Milky Way's dark matter like a spoon in thick syrup, creating ripples that amplify gravitational forces we don't yet understand. If true, the dwarf galaxy isn't just a passenger, it's an active participant reshaping the very forces that hold it captive. What makes this discovery so urgent isn't just the mystery of the present, but the implications for the future. The large Magellanic Cloud's velocity means it's transferring energy to the Milky Way's outer disk, potentially destabilizing stars at the fringes of our galaxy. Over billions of years, this gravitational tug-of-war could fling entire star clusters into intergalactic space, or even trigger new waves of star formation as gas clouds collide. It's a reminder that galaxies aren't static islands but dynamic ecosystems, where even the smallest players can rewrite the rules. The more we study this cosmic oddball, the clearer it becomes. The large Magellanic Cloud isn't just defying expectations, it's exposing gaps in our understanding of gravity, dark matter, and the delicate balance that binds galaxies together. Every new observation peels back another layer, revealing a universe where the unseen forces shaping our cosmic neighborhood are far stranger and far more influential than we ever imagined. The Virgo Cluster, a sprawling metropolis of over 1,000 galaxies just 55 million light-years away, should be drifting gently from us like every other distant structure in an expanding universe. But it's not. Instead, it's racing away at an astonishing 1,000 kilometers per second, nearly twice the speed expected from cosmic expansion alone. This isn't just a minor discrepancy, it's a glaring anomaly that suggests something massive, something unseen, is yanking the entire cluster off course. At the heart of the mystery lies the Virgo-centric flow, a vast river of galaxies all moving toward the same invisible point in space. Picture a cosmic conveyor belt, dragging everything in its path, including our own Milky Way, toward an unseen gravitational anchor. The problem: when astronomers tally up the visible mass in the Virgo cluster's vicinity, its galaxies, hot gas, and dust, it's nowhere near enough to explain this colossal pull. So what's generating the extra gravity? One leading theory points to the Great Attractor, the same mysterious force tugging thousands of galaxies toward the constellation Centaurus. But Virgo's motion is too extreme to blame on that alone. Some researchers speculate there's an even larger structure lurking behind it, a supercluster so immense it makes Laniakea look like a neighborhood. Imagine stepping back from a city skyline and realizing the tallest skyscraper you thought dominated the view is actually dwarfed by a hidden megastructure just beyond your line of sight. That's the scale we're dealing with. Then there's the dark matter angle. If the Virgo cluster sits at the intersection of multiple dark matter filaments, those invisible threads weaving the cosmic web, their combined gravity could be acting like a cosmic magnet, amplifying the cluster's motion. Simulations show these filaments might channel galaxies along specific pathways, creating flows like the one we're witnessing, but even this explanation has gaps. The velocities involved are so high they'd require dark matter to be clumped in ways we've never observed, or perhaps interacting with itself through forces beyond gravity. What makes the Virgo cluster's recession so baffling isn't just the speed but the implications. If our local patch of the universe is being dragged toward unseen mass, it means our measurements of cosmic expansion, the Hubble constant, might be skewed by these hidden currents. It's like trying to measure the speed of a river while unknowingly caught in a whirlpool. Some cosmologists argue this could even resolve the Hubble tension, the nagging discrepancy between different methods of calculating the universe's expansion rate. But the most tantalizing possibility is that we're glimpsing a flaw in our understanding of gravity itself. Could Einstein's equations break down on these colossal scales, requiring tweaks to account for Virgo's bizarre motion? Or is the universe playing a trick on us, hiding structures so vast they rewrite the rules of cosmic motion? Every telescope trained on this region, from radio arrays mapping hydrogen flows to space observatories tracing X-ray halos, brings us closer to answers. Yet with each discovery, the Virgo cluster whispers the same unsettling question. How much of the universe's dance are we still missing? One thing's certain, this isn't just about one cluster's odd behavior. It's a window into the hidden architecture of the cosmos, where gravity's reach extends far beyond what we can see. And as long as Virgo keeps defying expectations, it'll remain a beacon, guiding us toward the next great cosmic revelation. Stretching over 1 billion light-years across the cosmos, the Perseus-Pisces Supercluster isn't just a collection of galaxies, it's a cosmic freight train, barreling through space with thousands of galaxies moving in eerie unison. What's baffling isn't just its size, but its speed. This colossal structure defies expectations, racing through the universe at velocities that leave astronomers scratching their heads. Standard models predict that galaxies should drift apart gently, carried by the expansion of space itself. But Perseus-Pisces isn't drifting. It's surfing, caught in a current so powerful it hints at forces we've yet to fully understand. At the heart of the mystery is something called bulk flow, the idea that entire superclusters can move together, dragged by gravitational tides from even larger structures. Think of it like leaves floating on a river. Individually, they might bob and spin, but the whole current carries them in the same direction. For Perseus-Pisces, that river seems to flow toward something monumental, something beyond the edges of our maps. Early measurements suggest its motion aligns with other massive flows, like the mysterious dark flow detected in the cosmic microwave background, where clusters of galaxies appear to stream toward a distant, unseen attractor. Could these movements be connected? And if so, what's pulling them? One possibility is dark energy's invisible hand. If this enigmatic force isn't perfectly uniform, if it ebbs and flows like cosmic weather, it might create regions where space expands faster, tugging galaxies along for the ride. Picture a tablecloth with wrinkles. Where it's bunched up, objects slide unpredictably. But here's the catch: dark energy is supposed to act evenly, a smooth force accelerating the universe's expansion. For it to create these flows, we'd need to rethink its very nature, perhaps as a dynamic field with variations we've yet to detect. Then there's the shadow of the unseen. The Perseus-Pisces Supercluster might be responding to gravitational waves from the universe's infancy, ripples frozen into space-time during the Big Bang that still nudge galaxies into alignment. Or perhaps it's linked to an even grander structure, a supercluster, so vast it warps the motion of everything around it. Some theorists speculate about the Sloan Great Wall, a filament of galaxies even larger than Perseus-Pisces, whose gravity could be orchestrating these flows from afar. But the most tantalizing clue lies in the supercluster's own structure. Unlike chaotic galaxy clusters, Perseus-Pisces is remarkably ordered, its galaxies strung along filaments like pearls on a necklace. This suggests its motion isn't random but shaped by the cosmic web's hidden architecture, the dark matter scaffolding that guides galaxies into these vast rivers of motion. If we can decode its trajectory, we might unlock secrets about how the universe organizes itself on the grandest scales. What makes Perseus-Pisces so extraordinary isn't just its defiance of models, but the way it forces us to confront the limits of our cosmic vision. Every telescope trained on its galaxies reveals another layer of the puzzle, another thread in the tapestry we're only beginning to unravel. It's a reminder that the universe doesn't just expand, it flows, carrying entire superclusters in currents we're only now learning to trace. And with each new observation, we edge closer to understanding the invisible forces that shape not just this supercluster's journey, but the fate of everything in the cosmos. Nestled within the constellation Coma Borealis, the Coma cluster isn't just another gathering of galaxies, it's a cosmic demolition derby, where thousands of galaxies zip around at breakneck speeds, defying every expectation of gravitational etiquette. Normally, in a cluster this dense, galaxies should move at velocities balanced by the collective pull of their neighbors. But here, many are racing so fast they should have flown off into the void eons ago. Yet they haven't. They're trapped, as if some unseen force has woven an invisible net to catch them. This isn't just a puzzle, it's a glaring clue that the universe's hidden architecture is far more intricate than we've dared to imagine. The heart of the mystery lies in what astronomers call the missing mass problem. When scientists tally up all the visible matter in the Coma cluster, stars, gas, dust, it adds up to only a fraction of the gravity needed to keep these high-speed galaxies from escaping. So where's the rest coming from? The leading answer, of course, is dark matter, but the Coma cluster twists that explanation into something even more perplexing. The dark matter here isn't just a passive halo. It seems to be arranged in a labyrinth of filaments and knots, creating pockets of intense gravity that act like cosmic glue. Imagine a spiderweb where some threads are sticky enough to snag a speeding bullet. That's the kind of gravitational grip we're dealing with. Yet even this dark matter scaffold might not tell the whole story. Some galaxies in the cluster are moving too fast, even for the proposed dark matter distribution. One theory suggests the Coma cluster might be the product of a violent merger, where two smaller clusters collided and sent shockwaves rippling through their dark matter, leaving behind turbulent regions of amplified gravity. Picture two whirlpools crashing together. Their chaotic aftermath could create unpredictable currents, some strong enough to pin galaxies in place despite their velocity. Then there's the wild card. Dark matter might not be the only player. Could there be an unknown force, something beyond our current physics, adding extra tension to this cosmic web? Some researchers speculate about modified gravity theories, where the rules change in extreme environments like galaxy clusters. Others wonder if the cluster's central supermassive black holes, behemoths weighing billions of suns, are stirring the pot, their gravity creating localized eddies that alter the motion of nearby galaxies. What makes the Coma cluster so extraordinary isn't just the mystery of its runaway galaxies, but what it reveals about the universe's hidden frameworks. These aren't just random speedsters, they're test subjects in a grand experiment revealing how dark matter, or something even stranger, sculpts the cosmos on scales we're only beginning to map. Every observation peels back another layer, showing us a universe where the rules aren't just written in the stars but in the invisible threads between them. And with each discovery, we're forced to ask, how much of the cosmic tapestry are we still not seeing? Surrounding our Milky Way and its neighboring galaxies, there's an emptiness so vast it's hard to fathom, a cosmic bubble called the local void, stretching nearly 200 million light-years across. But this isn't just a passive absence of matter. It's an active force, shoving the entire local group of galaxies outward at speeds that defy the universe's uniform expansion. Imagine standing on a raft, not just drifting on a calm river, but being pushed by an invisible current stronger than the water's natural flow. That's the puzzle astronomers face when studying this void. The local void's behavior flips conventional cosmology on its head. According to standard models, empty regions should act like gentle dips in space-time, their lack of gravity allowing surrounding matter to spread outward at predictable rates. But here, the void isn't just letting galaxies move, it's propelling them, as if space itself is exhaling with unexpected force. Measurements show the local group is racing away from the void's center at over 250 kilometers per second, far faster than the universe's expansion alone can explain. So what's behind this cosmic shove? One theory points to dark energy's uneven influence. If this mysterious force isn't perfectly uniform, if it's stronger in voids than in dense regions, it could act like a cosmic pressure cooker, accelerating the expansion of empty space faster than cluttered areas. Picture blowing up a balloon with weak spots. The thinner rubber stretches more easily, creating bulges that push outward. But even this idea struggles to account for the sheer violence of the local void's push. Some simulations suggest the void might be emptier than we thought, a near-perfect vacuum whose lack of matter amplifies dark energy's effect to extreme levels. Then there's the ghostly hand of neighboring structures. The local void isn't floating in isolation. It's sandwiched between massive superclusters like Laniakea and the Perseus-Pisces filament. Their combined gravity could be squeezing the void, forcing it to collapse inward, not by pulling matter in, but by pushing space itself outward in a rebound effect. Think of a sponge releasing pressure after being squeezed, its springs flinging droplets in all directions. In this case, the droplets are galaxies, and the sponge is space-time. But the most tantalizing possibility is that voids like this one aren't just empty, they're active players in cosmic evolution. If their expansion accelerates galaxies, they could be sculpting the large-scale structure of the universe in ways we've barely begun to map. Every time we peer deeper into the local void's abyss, we're met with the same unsettling question. Are we witnessing a flaw in our models, or the first hints of a universe where emptiness holds just as much power as matter? What's clear is this: the local void isn't just a blank spot on the map. It's a dynamic force reshaping our corner of the cosmos and challenging us to rethink what it means for space to be empty. As telescopes grow sharper, this enigmatic region may yet reveal whether it's an outlier or a signpost, pointing toward truths hidden in the gaps between everything we see. The Sloan Great Wall looms across the cosmos like a titan of the deep, a filament of galaxies stretching nearly 1.4 billion light-years, making it one of the largest known structures in the observable universe. But size alone isn't what makes it extraordinary. This colossal ribbon of stars and dark matter isn't just sitting still. It's moving, and not in the gentle, predictable drift of cosmic expansion. Entire sections of this wall are racing through space at velocities that defy our models, as if tugged by invisible hands or pushed by forces we've yet to name. What's truly baffling is how this motion contradicts one of cosmology's bedrock assumptions, the cosmological principle, the idea that on large enough scales, the universe should look roughly the same in every direction. The Sloan Great Wall throws a wrench into that notion. Its motion isn't uniform. Some regions streak faster than others, creating a chaotic flow that suggests the universe's grand tapestry might be woven with uneven threads. Imagine a sheet of fabric billowing in the wind, but instead of fluttering evenly, parts of it snap and ripple with inexplicable energy. That's the kind of anomaly we're dealing with here. One possible explanation lies in the gravitational pull of neighboring superclusters. Think of the cosmic web as a vast network of rivers, with superclusters acting like massive whirlpools. The Sloan Great Wall could be caught in the currents of nearby giant structures like the Hercules-Corona Borealis Great Wall or the Perseus-Pisces Supercluster, their combined gravity warping spacetime enough to send this filament into motion. But here's the catch. Even when astronomers account for these known neighbors, the math still doesn't add up. The wall's speed hints at influences beyond what we've mapped, as if hidden leviathans lurk just beyond the edges of our charts. Then there's dark energy's role to consider. If this mysterious force isn't perfectly uniform, if it fluctuates like cosmic weather, it could create pockets where space expands faster, tugging structures like the Sloan Great Wall along for the ride. Picture blowing up a balloon with weak spots. Some areas stretch more than others, distorting the surface in unpredictable ways. But this theory, too, has its limits. Dark energy is supposed to act smoothly, a constant force accelerating the universe's expansion. For it to create these uneven flows, we'd need to rethink its very nature, perhaps as a dynamic field with variations we've yet to detect. The most tantalizing possibility, though, is that the Sloan Great Wall's motion isn't just about external forces. What if the structure itself is so massive that it warps the fabric of spacetime around it, creating its own gravitational currents? On these scales, the rules might change. General relativity predicts that colossal masses can bend light and twist time. Could they also generate self-sustaining motions, like a cosmic engine powered by sheer size? Some simulations suggest this might be the case, with the wall's dark matter scaffolding acting as a kind of conveyor belt, channeling galaxies along invisible tracks. What makes this structure so compelling isn't just its defiance of expectations, but the questions it forces us to confront. Are we seeing the limits of the cosmological principle, or is the Sloan Great Wall a signpost pointing toward something deeper, a universe where even the largest structures are subject to forces we've yet to imagine? Every telescope trained on its galaxies, every map of its sprawling filaments, brings us closer to answers, but for now it stands as a reminder: the universe doesn't just expand. It moves in ways that continue to surprise us, challenge us, and beckon us to look further. Centaurus isn't just another galaxy, it's a cosmic cannon, firing twin jets of plasma at nearly the speed of light from its monstrous central black hole. But when astronomers first measured these jets, they faced a paradox. The particles within them seemed to be moving faster than light itself. This illusion, known as superluminal motion, isn't magic, it's a trick of perspective, where material racing toward us at near light speed appears to outpace reality. Yet, even with this explanation, Centaurus A's jets remain some of the most extreme particle accelerators in the universe. pushing the boundaries of what we know about black holes and their violent surroundings. What makes these jets so mesmerizing isn't just their apparent speed but their structure. Stretching over 1,000,000 light-years, 10 times the diameter of our Milky Way, they're threaded with knots and filaments that flicker like cosmic Morse code. Each pulse reveals the black hole's feeding cycle as it shreds stars and gas, then belches their remains into space at nearly light speed. Imagine a tornado spinning so fast it flings debris beyond the horizon, except here, the tornado is spacetime itself, twisted by a black hole with the mass of 55 million suns. But the real puzzle lies in the jet's composition. They're not just hot gas, they're laced with ultra-high-energy cosmic rays, particles boosted to energies far beyond anything our most powerful colliders can produce. Some researchers suspect magnetic fields near the black hole act like cosmic slingshots, winding tighter and tighter until they snap, flinging particles outward with unimaginable force. Others speculate that jets might contain exotic matter particles that behave differently under extreme gravity, allowing them to skirt the usual speed limits. Then there's the black hole spin. Centaurus A's jets aren't chaotic. They're precision-guided, suggesting the black hole rotates like a gyroscope, its spin axis locked in place for millions of years. This stability hints at something profound. Black holes might not just be chaotic destroyers but cosmic engineers, shaping their surroundings with eerie precision. If we could decode the physics behind these jets, we might unlock secrets about how black holes mold entire galaxies over cosmic time. What makes Centaurus so invaluable isn't just its spectacle but its proximity. At just 12 million light-years away, it's close enough for telescopes to dissect its jets in unprecedented detail. Every observation peels back another layer, radio waves revealing the jet's magnetic skeletons, X-rays exposing their shock fronts, gamma rays tracing their most energetic particles. With each new dataset, we're not just solving a speed illusion, we're piecing together the operating manual for one of the universe's most powerful engines. And the more we learn, the clearer it becomes. These jets aren't anomalies, they're blueprints showing us how black holes write their rules on the fabric of spacetime itself. The universe is expanding, this much we know, but look closely and you'll notice something strange. Not all galaxies are playing by the rules. While most drift apart in the gentle current of cosmic expansion, some are sprinting ahead, their motion defying the steady rhythm we call the Hubble flow. These outliers, known as peculiar velocities, aren't just cosmic quirks, they're red flags, signaling that our maps of the universe might be missing entire continents of gravity. Take the Leo spur, a string of galaxies racing toward the Virgo cluster at nearly 700 kilometers per second. According to the Hubble flow, these galaxies should be drifting away from us at a predictable pace, carried by the expansion of space itself. Instead, they're being reeled in as if caught in a gravitational riptide. The culprit, likely the Virgo cluster's immense mass, its dark matter halo reaching out like an invisible hand to tug on everything in its vicinity. But here's the twist: even when we account for Virgo's pull, the math still doesn't add up. Some of these galaxies are moving too fast, as if another, even larger structure is hiding just beyond our sightlines. Then there's the case of the Milky Way itself. Our galaxy isn't just floating passively in the cosmic stream, it's hurtling toward the Great Attractor at over 600 kilometers per second, a motion that can't be explained by the Hubble flow alone. For decades, astronomers chalked this up to the gravitational pull of nearby superclusters, but recent surveys reveal a startling truth. The combined mass of these structures accounts for barely half the force needed to explain our galaxy's speed. So what's providing the extra push? One theory points to the Shapley supercluster, a behemoth 650 million light-years away, whose gravity might be reaching across intergalactic space like a cosmic leash. Others speculate about dark flow, a mysterious, large-scale current in the universe, hinted at by subtle ripples in the cosmic microwave background, dragging entire galaxy clusters toward some unseen attractor. But the most tantalizing possibility is that these anomalies aren't just about hidden mass, they're clues that our understanding of cosmic expansion is incomplete. The Hubble flow assumes space stretches evenly, like a rubber sheet inflating uniformly. But what if the sheet has wrinkles, regions where dark energy's push is stronger, or where space-time itself is warped by ancient gravitational waves? Some models even suggest that the universe's expansion isn't perfectly smooth, that on the largest scales it has a texture, with galaxies sliding faster along certain corridors of space. That's the real power of these cosmic rebels. They're not just breaking the rules, they're inviting us to rewrite them. Every galaxy that moves too fast, every cluster that tugs too hard, is a breadcrumb leading us toward a deeper truth about the universe's structure. And as telescopes grow sharper, these peculiar velocities may yet reveal whether we're missing matter, misreading gravity, or glimpsing something far stranger, a cosmos where expansion is just the beginning of the story. The Leo Ring is one of the universe's most baffling relics, a colossal loop of hydrogen gas stretching across 650,000 light-years, drifting in the cosmic void between galaxies. But this isn't just a wispy remnant of some ancient stellar explosion. It's racing through intergalactic space at nearly 200 kilometers per second, a speed that shouldn't be possible for something so diffuse and seemingly unanchored. If gravity alone were at work, this ring should have dissipated eons ago, its gas scattered into the darkness. Yet here it is, defying expectations, spinning like a cosmic lasso with no hand to swing it. What makes the Leo Ring so perplexing isn't just its speed, but its very existence. Gas clouds this massive usually belong to galaxies, either as fuel for newborn stars or as leftovers from collisions. But the Leo Ring floats in isolation, untethered to any visible structure. One theory suggests it's the shattered remains of a high-speed galactic crash, a wreck so violent it tore the gas from its parent galaxies and flung it into the void. Picture two cars colliding at such force that their spilled fuel forms a perfect, spinning circle midair before hitting the ground. That's the kind of energy we're talking about. Yet even this explanation falls short. Simulations show most collisions would leave gas clumpy and uneven, not woven into a smooth, coherent ring. Then there's the dark matter angle. Some astronomers propose the ring might be tracing the outline of an invisible filament, a river of dark matter flowing through intergalactic space, its gravity shepherding the gas into this bizarre formation. If true, it would be the first direct glimpse of the cosmic web's hidden scaffolding, a fingerprint of the universe's underlying architecture. But even this groundbreaking idea struggles to explain the ring's breakneck motion. Dark matter filaments are thought to move sluggishly, tugged by the slow dance of cosmic expansion. The Leo Ring's velocity suggests something far more dynamic, perhaps a recent, catastrophic event that set it spinning like a wheel kicked into motion. The most tantalizing clue lies in the ring's chemistry. Unlike typical intergalactic gas, it's rich in heavy elements, the kind forged in stars and scattered by supernova. This means it didn't originate in the primordial void but was once part of a living, stellar ecosystem. Was it stripped away by a near miss with a passing galaxy? Or is it the last echo of a dwarf galaxy torn apart by tidal forces, its stars long gone but its gas lingering like smoke after a fire? Every observation deepens the mystery. Radio telescopes tracing the hydrogen's faint glow reveal subtle ripples in the ring's structure, knots and braids that hint at turbulent origins. Meanwhile, optical surveys search for faint starlight that might betray a hidden galactic core, some unseen anchor holding this cosmic oddball together. So far, nothing. The Leo Ring remains a ghostly enigma, a reminder that the universe's most puzzling artifacts often lurk in the gaps between everything we think we know. What's clear is this: the Leo Ring isn't just a curiosity. It's a challenge, a cosmic riddle demanding we rethink how matter moves through the void. Whether it's evidence of dark matter's hidden choreography or the scar of a collision too violent to imagine, one thing's certain: the universe loves to surprise us. And as long as structures like this defy explanation, the night sky will always hold more questions than answers. The Fornax cluster might seem like just another gathering of galaxies at first glance, 60 million light-years away, home to a few hundred members and modest compared to cosmic giants like Virgo. But hidden beneath its unassuming appearance lies a gravitational enigma. The galaxies here are hurtling around the cluster's core at speeds that would send them flying into the void if only visible matter were holding them together. They're trapped unmistakably by something unseen. This invisible grip points to a dark matter halo so massive it should dwarf the cluster's luminous material. Yet when astronomers map its distribution, the puzzle only deepens. Dark matter isn't behaving the way simulations predict. Instead of forming a smooth, symmetrical cloud around the cluster, it's clumped in odd, lopsided patches, some regions dense with unseen mass, others strangely sparse. It's as if someone took a perfectly mixed batter and dumped it unevenly into a cosmic pan, leaving thick globs alongside thin stretches. This irregularity defies our best models of how dark matter should behave in such environments. If dark matter is truly cold and collisionless, as leading theories suggest, why isn't it settling into the expected, orderly halo? One possibility is that the Fornax cluster's history is messier than we thought. Galaxy clusters often grow by cannibalizing smaller groups, and each merger could stir the dark matter pot, leaving behind swirls and eddies in its wake. Imagine pouring cream into coffee. Gentle stirring creates smooth ripples, but a vigorous shake leaves chaotic blobs. Fornax might bear the scars of a violent past, its dark matter still unsettled from ancient collisions. Yet even this explanation has holes. Some of the clumps are too extreme, too sharply defined, as if dark matter is responding to rules we haven't yet written. Then there's the startling discovery of dark galaxies, dim, star-poor objects lurking in the cluster's outskirts, their mass dominated by dark matter. These ghostly islands might be the missing pieces of the puzzle, fragments of a larger structure that's been torn apart over eons. If so, they could trace the outline of the cluster's true dark matter skeleton, revealing how it stretches far beyond the visible galaxies. But here's the twist: these dark galaxies aren't distributed evenly. They cluster in ways that suggest dark matter might interact with itself, not through gravity alone, but through some faint, unknown force. The implications are profound. If dark matter can clump this unpredictably, it could reshape our understanding of how galaxies form and evolve. Maybe what we're seeing in Fornax isn't an anomaly but a signpost, a hint that dark matter is more complex, more dynamic than we've dared to assume. Every new observation, from gravitational lensing maps to the motions of star streams within the cluster, peels back another layer of the mystery. And with each layer, we're forced to confront a humbling truth. The universe's hidden scaffolding might be far stranger, far more intricate than our simulations have ever dreamed. The Sagittarius dwarf galaxy should be dead by now, torn apart by the Milky Way's gravity over billions of years. Its stars have been strewn across our sky in vast, looping ribbons called tidal streams, cosmic breadcrumbs marking its slow destruction. But here's what astronomers never expected. these streams aren't just drifting passively. They're racing around our galaxy at speeds that suggest an invisible hand is guiding them, something far more massive than the Sagittarius dwarf ever appeared to be. At the heart of the mystery lies dark matter. When scientists first mapped the dwarf galaxy's remnants, they assumed its original mass matched its visible stars, a modest collection barely 1/10,000th the Milky Way size. Yet the velocity of its tidal streams tells a different story. These stars are moving too fast, as if they're still tethered to something colossal. The math points to a dark matter halo that once enveloped the Sagittarius dwarf, a hidden gravitational anchor so dense it shouldn't exist for a galaxy of its small size. Imagine a tiny pebble tied to an invisible boulder. The pebble might be all you see, but the boulder's weight dictates how the whole system moves. This discovery flips our understanding of galactic cannibalism on its head. When large galaxies like ours consume smaller ones, the victims are supposed to be lightweight, their dark matter halos too diffuse to resist being shredded. But the Sagittarius stream's motion suggests its dark matter was stubbornly cohesive, clinging to its stars even as the Milky Way's tides pulled them apart. Some researchers speculate this could mean dwarf galaxies aren't just scaled-down versions of larger ones. They might be fundamentally different, with dark matter packed into tighter, more resilient configurations. Then there's the stream's bizarre structure. Unlike smooth, predictable debris trails, the Sagittarius streams twist into strange kinks and clumps, as if they've encountered invisible speed bumps along their orbit. One leading theory blames the Milky Way's own dark matter halo, which might be lumpier than simulations predict. Picture rolling a ball of yarn through a field of buried magnets. The yarn would snag in unexpected places, just like these stellar streams. Another possibility, the Sagittarius dwarf wasn't alone when it fell into our galaxy. It might have brought unseen companions, other dark matter-rich dwarfs whose gravity still tugs at the streams like ghosts haunting their own wreckage. What makes this cosmic crime scene so valuable isn't just the clues it offers about dark matter, but the window it provides into our galaxy's past. The Sagittarius dwarf is one of the Milky Way's oldest victims, and its streams encode a record of that ancient collision. By studying their speeds and shapes, we're not just solving a mass mystery, we're reading a diary of galactic violence written in starlight. Every new observation peels back another layer, revealing how the universe's invisible scaffolding shapes even the most violent encounters. And with each revelation, we're forced to ask, if something as small as a dwarf galaxy can upend our assumptions, what else is hiding in the dark? The Ophiuchus Supercluster doesn't just move, it charges, a titanic assembly of galaxies hurtling through the cosmos with the momentum of an entire universe behind it. Stretching over 300 million light-years, this colossal structure isn't drifting aimlessly in the cosmic tide. Instead, it's locked onto a trajectory so precise, so deliberate, it's as if something immense, something unseen, is reeling it in. And that's the problem. According to our best models, the universe should be expanding uniformly, with matter distributed evenly enough that no single direction holds more gravitational pull than another. Yet Ophiuchus defies this cosmic isotropy, its motion pointing toward a mystery we can't yet map. What makes this supercluster's behavior so unnerving isn't just its speed, but the scale of the forces required to move it. We're not talking about a gentle nudge from a neighboring galaxy cluster. Ophiuchus is being dragged, its trajectory aligned with other massive flows like the Great Attractor, a distant concentration of superclusters 650 million light-years away. But here's the catch, even Shapley's immense gravity can't fully account for Ophiuchus's velocity. The numbers demand something even grander, a gravitational anchor so vast it might lie beyond the edges of our observable universe. Picture standing on a shore, feeling the tide tug at your feet, only to realize the current isn't coming from the ocean you see, but from a hidden sea just over the horizon. Then there's the unsettling possibility that Ophiuchus's motion isn't just about gravity. Some theorists speculate these large-scale flows could be relics of the universe's infancy, echoes from the Big Bang itself, when quantum fluctuations etched invisible ripples into spacetime. These primordial wrinkles might have sculpted preferred directions for matter to flow, creating cosmic rivers that persist billions of years later. If true, Ophiuchus isn't just moving towards something, it's riding a current older than time. Yet the most tantalizing clue lies in what's not there. The region Ophiuchus is hurtling toward isn't empty, it's dotted with galaxy clusters and superclusters, but their combined mass falls woefully short of explaining the pull. This gap has led to radical proposals. Could dark energy, the force accelerating the universe's expansion, be unevenly distributed, creating pockets where its repulsive push weakens and gravity dominates? Or might there be a flaw in our understanding of how gravity operates across these staggering distances, a hidden variable that only reveals itself on scales larger than we've yet probed? Every telescope trained on Ophiuchus peels back another layer of the mystery. Gravitational lensing maps reveal dark matter's hidden scaffolding, while redshift surveys trace the supercluster's motion in 3 dimensions. But with each answer comes a deeper question, a reminder that the universe's grandest structures are still writing their own rules. Ophiuchus isn't just a supercluster, it's a compass pointing toward the gaps in our cosmic maps. And wherever it's leading, one thing's certain: we're only beginning to grasp the forces that steer the universe's mightiest giants. The Sexton's dwarf galaxy might be small, just a faint smudge of stars orbiting the Milky Way, but its motions tell a story that's anything but modest. Nestled in the constellation Sextans, this unassuming satellite galaxy should be a quiet backwater, its stars drifting lazily under the gentle pull of gravity. Instead, they're racing around their tiny galactic home at speeds that leave astrophysicists scratching their heads. According to our best models, these stars should have scattered into the void long ago, their velocities too great for the galaxy's meager visible mass to hold onto. Yet here they are, clinging stubbornly to their orbits as if tethered by invisible wires. The culprit, at first glance, seems obvious: dark matter. Like other dwarf galaxies, Sextans should be swimming in a halo of this mysterious substance, its gravity providing the extra pull needed to keep fast-moving stars in check. But when researchers calculate how much dark matter Sextans would need to explain its stellar motions, the numbers don't add up. The required halo would be so massive, so dense, that it defies simulations of how dwarf galaxies form. It's as if a tiny pebble weighed as much as a mountain, a discrepancy that shakes the foundations of our understanding. This anomaly has led some scientists to a radical alternative. Maybe dark matter isn't the answer at all. Enter modified Newtonian dynamics, or MUND, a theory that tweaks the laws of gravity to explain these odd motions without invoking unseen matter. In MUND framework, gravity behaves differently in the weak fields of dwarf galaxies, subtly strengthening just enough to hold their stars in place. Picture a river whose current mysteriously quickens in shallow stretches, no hidden forces, just rewritten rules. For Sextans, this could mean its stars aren't moving too fast, our equations are simply too rigid. Yet MUND has its own hurdles. While it neatly explains Sextan's stellar speeds, it struggles to account for other cosmic phenomena like the bullet cluster's separation of dark and visible matter without awkward adjustments. The debate has become a cosmic tug-of-war, with dark matter proponents pointing to MUND gaps, and MUND advocates highlighting dwarf galaxies like Sextans as glaring flaws in the standard model. What makes sextans so pivotal isn't just the mystery of its stars, but what it reveals about our methods. This tiny galaxy is a laboratory, testing the limits of our theories under extreme conditions. Every new observation, every flicker of starlight traced by telescopes adds another piece to the puzzle. Is sextans a sign that dark matter's distribution is stranger than we thought, or a clue that gravity itself plays by different rules on the universe's smallest scales? For now, the sextan's dwarf remains a cosmic enigma, its racing stars a silent challenge to our assumptions. Whether it's revealing hidden layers of dark matter or rewriting the laws of physics, one thing's certain: even the smallest galaxies can hold the biggest surprises. And as long as their motions defy explanation, the night sky will keep us questioning, probing, and wondering what else we've yet to uncover. The Pisces-Cetus Supercluster complex isn't just another cluster of galaxies, it's a cosmic metropolis. A sprawling web of galaxy filaments stretching over 1 billion light-years, weaving through the constellations of Pisces and Cetus like a hidden river of stars. But what's truly startling isn't its size, it's the way the entire structure seems to move, galaxies streaming along invisible highways with a coordination that shouldn't be possible under ordinary gravity alone. This isn't random drift. It's as if the universe has bones, an unseen skeleton guiding the motion of everything within it. At the heart of this mystery lies dark matter's grand architecture. The Pisces-Cetus complex isn't just a random assortment of galaxies. It's a junction where multiple filaments of the cosmic web intersect, funneling galaxies into flows that defy simple expansion. Picture a subway system where the tracks are made of gravity and the trains are galaxies hurtling toward hubs of unseen mass. When astronomers map the velocities of these galaxies, they find something eerie. Entire sections of the supercluster are moving in sync, as if tugged by a conductor's baton. The visible matter we see, the stars, gas, and dust, is just the echo of something far larger, far darker, orchestrating the dance from behind the curtain. Yet even dark matter's gravitational pull might not tell the whole story. Some regions within Pisces-Cetus are moving faster than the surrounding cosmic web should allow. One theory points to the Shapley supercluster, a gravitational titan nearly 700 million light-years away, whose influence might be reaching across the void like a cosmic tide. But here's the catch: Shapley's pull, while immense, can't fully account for the speeds observed. This discrepancy has led to wilder ideas like the existence of a supervoid, an enormous bubble of near-nothingness on the far side of Pisces-Cetus, whose lack of gravity might be effectively pushing the supercluster away. Think of it like a ship caught between two currents, one pulling it forward, the other sucking the water out from behind. Then there's the spine-tingling possibility that we're seeing the imprint of the universe's infancy. The Big Bang didn't just create matter, it sent shockwaves through space-time, ripples that could have seeded preferred directions for matter to flow. Pisces-Cetus might be riding one of these ancient waves, its motion less about what's pulling it now, and more about how space-time itself was stretched 14 billion years ago. If true, this supercluster isn't just a structure, it's a fossil, preserving the universe's earliest moments in the trajectories of its galaxies. What makes Pisces-Cetus so extraordinary isn't just the scale of its mystery, but what it reveals about our place in the cosmos. We're not just observers of the universe's visible splendor, we're detectives piecing together clues from the silent, invisible forces that shape everything. Every galaxy in this supercluster, every filament in its web, is a breadcrumb leading us closer to understanding the universe's hidden blueprint. And with each new map, each deeper survey, we're reminded the cosmos doesn't just exist. It moves, it breathes, and it's waiting for us to decode its secrets. The Antlia II Galaxy shouldn't exist. Floating on the outskirts of the Milky Way, this ghostly dwarf is so faint it was only discovered in 2018, lurking in the shadows like a cosmic specter. But what makes Antlia II truly bizarre isn't just its elusiveness, it's the way its stars are moving. They're racing through space at velocities so extreme, they should have torn free from the galaxy's feeble grip long ago. Yet somehow, against all odds, Antlia II holds on, a shimmering enigma wrapped in dark matter's tightest secrets. At first glance, this dwarf galaxy looks like any other, a sparse collection of ancient stars, barely a wisp against the Milky Way's brilliance. But when astronomers measured its stellar motions, the numbers sent shockwaves through astrophysics. Antlia II stars are darting around at speeds that defy its visible mass, implying it must be anchored by something unseen. The math suggests a dark matter halo hundreds of times denser than expected for a galaxy this size, a gravitational scaffold so robust it's rewriting the rules of how dwarf galaxies form. Imagine a balloon filled with lead weight. Its surface might look ordinary, but the hidden mass inside would make it behave in ways no ordinary balloon could. But here's where the mystery deepens. If Antlia II is packed with this much dark matter, why is it so diffuse? Most galaxies with comparable dark matter halos are compact, their stars huddled close under the weight of that invisible gravity. Antlia II, by contrast, is sprawling, its stars scattered across a volume nearly as wide as the large Magellanic Cloud, despite containing just 1/10,000th as many stars. It's as if someone took a galaxy's gravitational engine and stretched it like taffy, leaving the stars adrift in a vast, invisible net. One theory suggests Antlia II might be the remnant of a violent encounter, a dwarf galaxy that strayed too close to the Milky Way eons ago and was stripped of most of its stars, leaving behind a dark matter core cloaked in tattered starlight. Simulations show such collisions could stretch a galaxy thin while preserving its dark matter heart, like pulling apart cotton candy but leaving the stick intact. Yet even this dramatic origin story struggles to explain the galaxy's extreme velocity dispersion. Some stars are moving so fast they'd escape even the proposed dark matter halo, unless that halo is shaped in ways we've never seen, perhaps flattened like a disk or threaded with unseen filaments that act like cosmic bungee cords. Then there's the radical possibility that Antlia II isn't a galaxy at all, but something stranger, a primordial dark matter clump that only accidentally collected a handful of stars. In the early universe, such clumps are thought to have formed before normal matter had time to coalesce. Most were absorbed by larger structures, but a few, like Antlia II, might have survived as dark matter fossils, their gravitational wells shallow enough to trap only the occasional star. If true, this ghostly dwarf could be a living relic of the universe's first moments, a time capsule holding clues about how dark matter shaped the cosmos before light even existed. Every telescope trained on Antlia II peels back another layer of its mystery. Spectrographs dissect the light of its stars, searching for chemical signatures that might reveal its origins. Astrometric satellites trace their motions in 3 dimensions, mapping the contours of its invisible halo. And with each new dataset, the same unsettling question lingers. Is Antlia II a freak accident, a cosmic outlier, or a signpost pointing toward a deeper truth about dark matter's nature? For now, this phantom galaxy remains a riddle, its existence a quiet challenge to our models of cosmic evolution. But one thing's certain, in the shadowy fringes of our galactic neighborhood, the universe is still hiding surprises, and Antlia II is proof that sometimes the most profound mysteries are the ones we almost missed. The KBC void isn't just empty space, it's a cosmic vacuum so vast it's warping the motion of our entire galactic neighborhood. Named after astronomers Keenan, Barger, and Cowie, This spherical underdensity stretches over 2 billion light-years, a staggering bubble of near-nothingness where galaxies are few and far between. But its emptiness isn't passive, it's actively pushing. The Milky Way and its neighbors in the local group aren't just drifting with the universe's expansion. They're racing away from this void at speeds that defy conventional models, as if repelled by some invisible force. At first glance, this seems counterintuitive. How can nothing influence something as massive as a galaxy? The answer lies in gravity's absence. In a universe where matter pulls, voids push. Picture a ball rolling downhill. Matter-rich regions act like valleys, their gravity drawing everything inward, while voids behave like peaks, creating slopes that send galaxies sliding outward. The KBC void's sheer scale amplifies this effect. With so little matter inside, the surrounding universe's collective pull isn't balanced, leaving our local group caught in a lopsided tug of war. The result, we're hurtling toward the denser Shapley supercluster at 600 kilometers per second, a motion the void's repulsive influence might help explain. Yet the KBC void's existence is itself controversial. Some astronomers argue it's a statistical fluke, a random gap in the cosmic web that only appears significant from our vantage point. Others counter that its underdensity is too extreme, too perfectly spherical to be accidental. If they're right, this void could be a relic of the universe's infancy, a frozen bubble from the Big Bang's primordial chaos. Quantum fluctuations in those first moments might have stamped some regions with extra density future galaxy clusters, while leaving others eerily bare. The KBC void wouldn't just be empty, it'd be a fossil, a whisper from the universe's first trillionth of a second. What makes this cosmic blank spot so pivotal isn't just its influence on our motion, but what it reveals about dark energy. If the void's repulsive effect is stronger than predicted, it might mean dark energy isn't uniform but clustered, its push varying across space like cosmic weather. Alternatively, the void could hint at flaws in how we model gravity on the largest scales. Einstein's equations assume a smooth universe, but what if space-time is lumpier than we thought, with voids and filaments bending its rules in ways we've yet to grasp? Every new galaxy survey adds another piece to the puzzle. Telescopes like Euclid and the Vera Rubin Observatory are mapping the void's edges, searching for subtle distortions in starlight that might reveal its true shape and mass or lack thereof. The stakes couldn't be higher. If the KBC void's influence holds up, it could rewrite our understanding of cosmic motion, proving that nothing might be just as powerful as everything else. And if it's just a mirage, well, that would mean something even stranger is yanking our galaxy off course, a mystery waiting in the darkness beyond the void. The dark flow is one of the most unsettling mysteries in modern cosmology, a river of galaxy clusters all streaming in the same direction, as if pulled by something beyond the edge of everything we can see. It started with subtle anomalies in the cosmic microwave background, the afterglow of the Big Bang. When scientists mapped the motion of hundreds of galaxy clusters, they found something impossible. These massive structures weren't just drifting with the universe's expansion. They were hurtling toward a single point in space at speeds exceeding 1,000 kilometers per second. A movement so coordinated it defies everything we know about cosmic structure. What makes this discovery so controversial isn't just the motion itself, but where it's pointing. The dark flow's trajectory suggests an attractor so distant, so unimaginably vast, that it lies beyond the observable universe. That's not just speculation, it's a direct challenge to one of cosmology's foundational principles, the idea that the universe is homogeneous on the largest scales. If the flow is real, it implies an unevenness to reality itself. a cosmic lopsidedness where structures outside our horizon wield gravitational influence we can detect but never directly observe. Skeptics argue it could be a measurement error, a quirk of how we interpret the motion of hot gas within galaxy clusters, but the data persists even after repeated analyses. Supporters of the dark flow hypothesis propose mind-bending explanations. Perhaps our universe is a bubble among others in a multiverse, and the flow is the gravitational tug of a neighboring cosmos. Or maybe the attractor is a relic of the pre-Big Bang universe, a scar from an earlier phase of existence that still echoes in the motion of galaxies today. The implications are staggering. If confirmed, the dark flow wouldn't just rewrite our maps of the cosmos, it would shatter the boundary of what we consider knowable. It's a reminder that the universe, vast as it is, might still be just a fraction of something far grander, a single note in a symphony we've only just begun to hear. And until we unravel its secrets, this enigmatic current will keep pulling at the edges of our understanding, daring us to look beyond the horizon. The cosmic microwave background, the afterglow of the Big Bang, should be a nearly uniform tapestry of heat, a relic of the universe's fiery birth. But nestled within this ancient glow lies an anomaly so chilling it defies explanation, the CMB Cold Spot. Stretching across 1 billion light-years, this region is colder than its surroundings by a fraction of a degree, a tiny difference, but one that sends shockwaves through cosmology. At first glance, it might seem trivial, yet this frigid patch is anything but ordinary. It's a cosmic paradox, a flaw in the universe's otherwise flawless fingerprint, and it might just rewrite everything we think we know about reality. One leading theory blames a supervoid, an enormous, underdense region of space where galaxies are scarce. Voids typically cool light passing through them via the integrated Sachs-Wolf effect. Photons lose energy as they climb out of these gravitational valleys, leaving the CMB slightly colder in those directions. But here's the catch: the cold spot's temperature drop is too extreme for any known void. Even the largest observed supervoids can't account for the anomaly's depth and scale. It's like finding a freezer in the desert. There's no power source big enough to explain it. This discrepancy has led to wilder possibilities. Could the cold spot be a bruise from a collision with another universe? Some theorists propose it's the imprint of a bubble universe brushing against our own in the multiverse's foam. It's exotic physics leaving a shadow on the CMB. Others suggest it might be evidence of a cosmic defect, a texture in spacetime itself, a frozen knot from the universe's earliest moments when fundamental forces hadn't yet settled into their current forms. Picture a crack in a frozen lake, a flaw in the ice's perfection, except here the ice is spacetime and the crack is 1 billion light-years wide. Yet skepticism lingers. Critics argue the cold spot could be a statistical fluke, a random fluctuation in the CMB's noise. After all, in a universe as vast as ours, even the most improbable patterns might appear somewhere. But the odds are slim. Calculations suggest there's only a 1 in 50 chance of such an anomaly arising by accident. That's not quite proof, but it's enough to keep scientists digging. The cold spot's true power lies in its ambiguity. It refuses to fit neatly into any single explanation, dangling between the known and the unimaginable. With every new observation, from galaxy surveys mapping the void's true extent to precision measurements of the CMB's polarization, we're forced to confront the limits of our models. Whether it's a window into the multiverse, a relic of primordial chaos, or simply a cosmic illusion, one thing's certain: the universe loves to unsettle us. And in that unsettling, we find the thrill of discovery, the chance to glimpse, however faintly, the truth still hidden in the cold. These cosmic speed demons aren't just breaking rules, they're tearing up the physics playbook entirely. Take Einstein's theory of relativity, the bedrock of modern cosmology. It's been tested to exquisite precision, from GPS satellites to black hole shadows. Yet when confronted with galaxies racing faster than visible matter should allow, the equations start to wobble. It's not that relativity is wrong, it's that the universe might be playing a more complex game than we realized, one where dark matter and dark energy hold wild cards we've yet to decipher. Consider dark matter first. For decades, we've treated it as a simple, passive scaffold, an invisible glue holding galaxies together. But the motions of these 26 cosmic rebels suggest something far stranger. The way galaxy clusters like Bullet or Coma fling their members around implies dark matter might interact with itself through unknown forces, or clump in ways our simulations never predicted. Imagine discovering that the silent partner in your business isn't just an investor but an active CEO making decisions behind the scenes. That's the scale of reassessment we're facing. Then there's dark energy, the enigmatic force accelerating the universe's expansion. Most models assume it's uniform, a smooth, ever-present push. But when voids like Boötes or KBC shove galaxies faster than expected, it hints dark energy might be lumpy, stronger in some regions than others. Picture blowing bubbles in a drink. Most rise steadily, but some surge unpredictably where the fizz concentrates. If true, we're not just misjudging the universe's speed limit, we've misunderstood the engine entirely. This is where radical theories enter the fray. Modified Newtonian dynamics, MUND, once a fringe idea, gains traction every time a dwarf galaxy like Sexton's defies dark matter expectations. By tweaking gravity's laws on cosmic scales, MUND attempts to explain odd motions without invisible matter. Yet even it stumbles before colossal anomalies like the Hercules-Corona Borealis Great Wall. Perhaps the answer isn't choosing between dark matter and modified gravity, but blending both or inventing something entirely new, the most thrilling possibility. These anomalies might be cracks in our models, revealing deeper layers of reality. Just as Mercury's wobbly orbit hinted at general relativity, today's cosmic speedsters could point toward quantum gravity, extra dimensions, or even holographic universe theories. The Pisces-Cetus Supercluster's coordinated flow or the dark flow's impossible pull might be the first whispers of physics beyond Einstein, a paradigm shift waiting in the data. What's at stake isn't just academic. Decoding these motions could redefine the universe's fate. If dark energy varies, the cosmos might not end in a cold, even expansion but a chaotic shredding. If dark matter interacts strongly, galaxies could collide in ways we've never simulated. Every rogue cluster, every overeager void is a clue, and right now, the universe is daring us to think bigger. The next physics revolution won't come from a lab or a chalkboard. It's written in the stars, racing past boundaries we once thought absolute. From quasars that appear to outpace light to galaxy clusters hurtling toward unseen horizons, these 26 cosmic rebels aren't just outliers, they're invitations to rethink reality itself. Each one whispers the same humbling truth: the universe is far stranger, far more dynamic than our textbooks ever dared to suggest. What makes these anomalies so electrifying isn't just that they break the rules, it's that they point to the gaps in our understanding, the places where the next great discoveries lie waiting. Take dark matter. For decades, we've treated it as a silent partner in cosmic evolution, a passive glue holding galaxies together. But the way the Bullet cluster's dark matter races ahead of visible gas, or how the Sagittarius dwarf stars cling to orbits they shouldn't, suggests something far more intricate. Maybe dark matter isn't just a backdrop, it could be an active player, clumping in ways we haven't predicted, interacting through forces we've yet to name. And what about dark energy? The local void's violent push and the KBC void's repulsive grip hint that this mysterious force might not be uniform at all. It could ebb and flow like cosmic weather, sculpting the universe in ways we're only beginning to trace. Then there's the biggest question of all: are we missing something even more fundamental? The dark flow's impossible pull toward the unobservable universe, the Hercules-Corona Borealis Great Wall's defiant scale. These aren't just puzzles. They're potential cracks in our models, signs that relativity might need revising, or that hidden dimensions could be warping space-time in ways we can't yet measure. Imagine living in a world where gravity was just a theory scribbled in Newton's notebook, and suddenly seeing Mercury's orbit wobble in ways that didn't fit. That's where we are now. These anomalies are our Mercury moments, clues that the next physics revolution is hiding in plain sight. The beauty of these cosmic speedsters is that they refuse to let us get comfortable. Just when we think we've mapped the universe's rules, a quasar's superluminal jets or the sexton's dwarf's rebellious stars force us back to the drawing board. And that's how science should be, not a static set of answers, but a living, breathing quest for deeper truths. With tools like the James Webb Space Telescope and next-generation radio arrays, we're on the verge of breakthroughs that could rewrite entire chapters of cosmology. So the next time you look up at the night sky, remember, those distant lights aren't just stars. They're part of a cosmic drama, a story where the fastest, wildest, and most mysterious players might hold the keys to everything we don't yet understand. If this journey through the universe's greatest speed demons left you as awestruck as we are, hit that like button, subscribe for more deep dives into the cosmos's secrets, and drop a comment below. What's the anomaly that blew your mind the most? The universe is vast, unpredictable, and endlessly surprising. And thanks to these 26 rule breakers, we know the adventure is just beginning.